Check. All right. Okay. At this point, we're getting there. We'll get something done today. All right. And I might use Bryce's hip chat link here because I can't get mine to work. Bryce, good idea. All right. Still logging into Bryce's chat room. Brodsky B at West Hampton Beach Schools.org. Job title, I'm a fly. Oh, excuse me, full name. Didn't like that email address. All right. I guess at least I have, I don't know what I'm doing here, but let's just try to go back to the room. All right. So we have 4 viewers. Let's do this. Okay. Let's start again with our homework. And I'll make some important points. This time you'll hear me say them. All right. So we're going to start with the homework. I'm going to share my screen and pull up the homework, either reboot my computer with some problems. So I'm going to share my screen. It's going to look weird for a second. And I'm going to pull up the homework, which was bonding intermolecular attractions. Let's do the key. Okay, so we should be all set. Everyone can hear me. And I'm going to start again. Okay, so what we're talking about are the attractive forces between molecules. And again, if you have not done your due diligence and listened to the lecture, which is something I taught you last year, then you're really going to be behind a little bit. But what we're talking about specifically are attractions between molecules. Now, molecules represent nonmetals, bonded to nonmetals by the covalent bonds. So we're talking about these attractive forces. They're never going to be as strong as our bonds, but they become very significant. And so we're talking about nonmetals, bonded to nonmetals. We're talking about essentially 4 different attractive forces, okay? And the first is, of course, our LDFs, London dispersion forces. And that's a really important one. 2 dipolar forces, and that's just the attraction between the positive end of one molecule with the negative end of another. And of course 3, and that's H bonding. Although bonding's in the word, we should all know that's really an attractive force. It's one of the strongest attractive forces because we're dealing with something called an electron deficient hydrogen, which is essentially a proton, okay? Now, when we evaluate these types of attractive forces in our molecules, covalent compounds, we always see the London dispersion forces generally are the weakest dipolar or second, and hydrogen bonding is the strongest. But I will have you understand that London dispersion forces, although considered the weakest, can become very significant. In fact, in some cases, can be more significant than dipolar forces. So don't fall in love with the fact that these are just weak little forces. Okay. Now, when we think about London dispersion forces, we think about an electron cloud of electrons. And because they're nonmetals, electrons are held pretty tightly. They're not usually delocalized. They're very localized. However, this electron cloud around the molecule can move a little bit. And because there is some opportunity to move, and it can't move a lot because, again, because of the strong, effective nuclear charges of nonmetals, they don't have that opportunity, but they can shift a little bit. And they shift a little bit. They make momentary dipoles, momentary. Okay, and I went over that explicitly in the lecture, so I'm not going to revisit that. But every molecule has London dispersion forces. So when I look at butane, methyl ethyl ether, acetone, when I look at them, now, of course, I'm showing you the backbone structures. There's a carbon at every ending and every corner, and they don't draw the H's. So this is basically the carbon structure. And then there's an oxygen here instead of the carbon. But essentially, we have this very similar structure and essentially the same number of electrons in all three. Now, it's important to realize the number of electron will also drive the strength of these momentary dipoles. The more electrons you have, the greater the effect of those very, very small shifting of electrons. So if you have more electrons, that means more electrons can make a greater negative size when they shift very, very slightly. And if they shift very slightly, and there's a lot of them, they make a stronger positive side. Now, again, these sides don't stay this way. They're not permanent dipoles, and they shift according to where other molecules or ions are making them. But the more electrons, the stronger. So butane, methyl ethyl ether, and acetone all have the same, approximately same number of electrons. So therefore, they have very, very similar LDF effects because of that cloud. Now, as I also said, they have very similar shapes. And because they have similar shapes, the electron cloud does not get affected. Now, I talked about this. The longer the molecule, the more elongated the electron cloud, the greater the shifting. There's an opportunity for electrons to shift and make a negative side or a positive side the longer the molecule. Okay, the more branching that occurs, the more rounder the molecule, okay, the less chance. So we talk about polarizability was the word that I used, and something you need to work, because this is a descriptive part of chemistry. You will see questions on this type of thing. They love to talk about talking about the attractive forces. So if you look very carefully, butane, methyl ether, and acetone, well, mostly butane and methyl ethyl ether, okay, have very similar shapes. And because it's similar shapes, they have, okay, very similar types of London dispersion forces along with their equal number of electrons. Now, acetone is less polarizable because of its shape. It's branched. It has the same number of electrons, but it's not going to have as strong as London dispersion forces. So if I was to ask you, and I did, who would have the weakest dispersion forces, you would say acetone, because it's less polarizable. This rounded shape doesn't give a nice place to make a strong negative. When you're a longer molecule, you can. So this is less polarizable. However, the question states, explain the trend in boiling points between butane, methyl ethyl ether, and acetone. Very clearly, they all have London dispersion forces, okay? Probably acetone has weaker, but methyl ethyl ether, because of this oxygen, creates a polar molecule. So it's got a negative end probably on the oxygen end, and some negative and some positive end somewhere. So this has what we'd say dipolar forces. So methyl ethyl ether has the same dispersion forces, but has an additional what? Dipolar force. Now, acetone is polar. It has London dispersion forces, but they're probably going to be weaker. But it's got a large dipolar force. And you'd probably say that it's, because of its shape, more polar than methyl ethyl ether. So we would probably say that acetone has a, or you'd say that methyl ethyl ether has a greater boiling point, which means it takes more energy to separate them because the attractive forces are stronger. But you can't say attractive forces are stronger. What you need to say is that methyl ethyl ether has an additional attractive force that butane doesn't. They both have lone dispersion forces, but methyl ethyl ether also has polar or dipolar forces. Acetone has on the dispersion forces, and it has a dipolar force, but you can make the case that it's more dipolar because this O creates more asymmetry. Okay? You can't say it has H bonds because there's no H attached to this O here. So acetone has a additional attractive force than butane, but is higher than methyl ethyl ether because its dipolar forces are greater. It's more polar. Okay? And let's see if we understand that correctly. I don't know what just happened there. Screen share my screen. Don't know if there's any questions. I'm in the dark here. And I'm assuming you can't chat with me here. I'm just gonna say hello, so anyone can hear me, see me. Any questions? I hate being like this. I don't know if I can hear you guys actually either. Not a darn thing. And let me just check the chat page. Make sure that we're on the same page here. Nothing. All right, I can keep going. Just gonna fly in the dark, I guess. All right, continuing on. Let's go back to screen share. Share that screen, boom. Okay, so here we go. Moving on. So I said all three have the same similar number of electrons. Butane, methyl, ethyl have the similar shape, thus have very similar dispersion to the polarity of the ether. It will have a dipolar force in addition to the same dispersion forces. All right, we kind of went over that. Okay, number two, which of the following systems will hydrogen bonding play an important role? Now, hydrogen bonding, again, it implies bonding, but I can't say enough. You have to think of this in terms of an electron deficient hydrogen. That's the way you want to say this, electron deficient. For instance, if I have hydrofluoric acid, HF, clearly the fluorine's much more electronegative and pulls the electrons closer. You know that hydrogen has one electron and one what? A proton. So when you think about the Lewis dot diagram, that is just a proton sitting out there. So in any case, you got to figure out whether or not who's got electron deficient hydrogens. All right, so in this molecule right here, we have no electron deficient hydrogens. This F is connected by a C. There is no H bonding here. All right, these H's, although probably have some electron drift, they need to be hooked up with, as I said yesterday, NOF, nitrogen, oxygen, and fluorine, the most highly effective nuclear charge or electronegative atoms that are small enough, okay? So no H bonding. Clearly, same idea here. All the hydrogens are connected to carbons. These elements are not electronegative enough to create that proton scenario. Now here, you have an H connected to oxygen, which creates that exposed proton. So this will H bond with itself or other compounds. Ammonia has electron deficient H's because the N is electronegative enough to expose the protons. Okay, so you're looking for an H in a polar molecule bonded with NOF that will create that electron deficient H's. Acetone does not H bond with itself, okay? And of course, if something like acetone, okay, dissolved, and this is the question here, NH3 dissolved in acetone, that's what this was, there will be attractive forces, and you will have H bonding with acetone. The electron deficient H of the ammonia will attract that end, all right? So even though this doesn't H bond with itself. It could in fact H bond with an electron deficient H of another molecule. Important to realize that moving forward. Okay, explain the following difference in the boiling points. Well, krypton, I should say, boils at -52. We know it's a gas at room temperature. It doesn't bond with anything. It's just an atom, so it's nonpolar. So it has London dispersion forces. Okay. And propane boils at -42. Well, propane is more polarizable because it's a what? A longer molecule, C3. Okay. It probably has very similar number of electrons, being that krypton is a big atom, but because of propane's elongated shape, the electrons are able to have an axis to move towards. So that's why this molecule. Now the next question was CH3,4. So this molecule here is at 10 degrees and carbon tetrachloride 77. They're both nonpolar, very symmetrical distribution of charge, no dipole moments here. Okay. But you would say that this molecule has more polarizability, even though the shape is the same, because of the higher number of electrons that chlorine has compared to the methyl end. There's more electrons that can shift, and that's what gives it its larger polarizability, or in this case, larger temperature. Now, as I said here, n = 3 orbitals, and they have more unbonded valence electrons, gives it larger polarizability. But bottom line is more electrons. Okay, so I like the more electrons better than this. All right, and N2 is liquid nitrogen is -196, and carbon monoxide is -191. All right, well, we definitely London dispersion forces are occurring here, but this is a polar molecule. So it's got London dispersion forces and it's got dipolar forces. And you can use the word polar forces. Okay. So this has an extra attractive force, which makes its, don't get crazy with the negative numbers, makes it a warmer temperature, a higher temperature. Not much, not greatly. And the reason why it's not tremendously a polar molecule, because of there's resonance within this compound, very complex structure. And because of the resonance, it actually kind of almost makes this nonpolar. There's a slight polarity here. Not as much as you'd expect because of the resonance. But in any case, the extra polar force makes the boiling point warmer. Okay, you have to understand that we're usually just adding an extra force. Classic example, this is just LDFs. This is LDFs N. So the extra force is what makes the boiling point go up, or the attractive force sometimes stronger. Acetone and methanol have nearly equal boiling points. Okay, well, look at this molecule and this molecule. What types of intermolecular forces does each exhibit? Well, if you look at acetone, as we talked about, it's a really important solvent in organic chemistry because it's got a polar end, and also it's got a great number of electrons in this chain here that can contract to nonpolar. So it's a very important solvent. Any case, it's got LDFs. Everything's got LDFs. So does CH3. Now, with itself, as we're talking about here, there's dipolar forces, as I am writing next to what's already written. Okay. Now, if you see methanol, it's got LDFs, probably not quite as strong. But because of this OH group we call hydroxyl group, it's got dipolar forces. And it can also what? H bond with itself. So by adding an extra bond here, or I should say attractive force, they both have LDFs, they both have dipolar, but because methanol has an additional attractive force called H bonding, it has a higher boiling point. All right. So here's the question: what types of, okay, now we figured out how they're different. What does the similarity in boiling points tell you about the relative magnitudes of each type of these forces? Well, if they have nearly the same boiling points, as I just said, and this has hydrogen bonding, this doesn't, there must be stronger forces of attraction in other areas. Okay, so I said here the dispersion forces and dipolar forces in methanol are lower. And I would guess that too because they have less electrons, okay? So the lower number of electrons, and because it's not as polar as that lower number of polarity is offset by the H bonding, okay? So not sure about the polarity part. I'm not sure if you can guess that, but definitely dispersion forces are going to be lower, okay, in the methanol than in the acetone. And then, of course, that difference is made up by what the acetone does not have, and that's H bonding. All right. Now, this last one was probably one that's a little unfair right now, but it's on the last part of the slideshow, and I'll go over that in a second. We're at the point now we're talking about types of compounds. We have arsenic, germanium, melts at 1210. Its other name is selenium, melts at 490. So we're going across the periodic table. We have arsenic, we had germanium, and then we had, so we're on the same N number here. So why are we going from 1210, I guess these are about the same thing, and then 490? Why is there a huge drop off? All right, well, germanium, as I said, is a metallic compound, has that sea of mobile electrons. And again, if I had those movies given to you in the presentation, you should have played them if you go through them. But we're going to say it's metallic bonding. Now, how do I know? Tremendously high melting point. Okay. Now, selenium has a higher melting point than expected for things that we consider to be nonmetals. Okay. Now, why? Well, why is it higher than I expect? Well, it must be that selenium is making a network of covalent bonds. So network solids are crystal forms of nonmetals. For the most part, things that make crystals are metals and ionic compounds. And because of those crystal lattices, they have high melting points. But we have some nonmetals that when made crystals, and a crystal would be that, like for instance, diamond bonds to other carbons in a tetrahedral format, and basically the tetrahedral bonds occur in all directions for other carbons, and that creates a network solid as well. So a network is basically covalent bonds. Silicon carbon is another example, and then diamond. Okay, these are the three most famous examples of nonmetals that will bond to themselves in a continuous fashion in all three dimensions. Okay, so I want to go to our I want to go back to screen share. Hold on, that screen, and I want to go to the our class web page and see my smiling face. Great. And I'm going to go to our intermolecular forces of attraction, looking at H bonds, and go here. So we have things called molecular compounds, which are covalent compounds, right? They make molecules. We have London dispersion forces, and they have what? Very low energy levels, although they can become significant. Look at the energy level in kilojoule per mole. It can go up to 40, okay? And molecular, that can go up to 25. So there's some cases where you can have dispersion forces that are greater than, okay, than just dipolar, okay? Look at the 40 here, and H bonding. There could be some weak H bonding. So even though we say dispersion forces are weak, they can match some of the polar and H bonding of some compounds. All right, now look at the melting points that go up. Metallic, we should know, is delocalized bonding of metals. The melting points are tremendously high. Ionic are very high, sometimes much higher because of the positive negative structure. And then we have the what? Covalent compounds that make bonds in all directions. Remember, the crystals that we have, especially for ionic, are just positives and negatives and positive negatives. For metallic, it's that face-centered close cubic packing that we've talked about, or body center, doesn't matter. These electrons are in a C, and what's in a crystal is the nuclei. What's in a crystal for network is going to be nonmetals bonded in all directions, and their melting points, okay, will be very high for covalent compounds. Normally, covalent compounds have low melting points, but in the small cases, and there's not too many of them, where you have a high melting point for nonmetals, that's telling you that you must have this network like a diamond. Okay, that's all I'm going to do today, and you have a homework. I want you to do the worksheet that you printed out, and I want you to start looking at the lectures for tonight. I'll list the homework specifically. Thanks for hanging in there with me today. Bye.